Okay, today we're going to talk about electric current. So when we talk about electricity and we talk about things moving, we're referring to the current. The current is what's moving through the wires. So electric current, the flow of charged particle. When you think about flow, you think about like a rate. Okay? So first of all, current is the charge per unit time, which we learned before, which is a coulomb per second. That makes sense because anything that's flowing, if it's a rate, it's going to be something per second. So the unit of current is an ampere, and we just call it for short an amp. So the symbol is capital I for current, and the unit is ampere. And in the little picture, you see how, because current, which is the flow of electrons, you see it's how many electrons are moving per second, and that makes sense. So I is equal to, again, the charge per unit time, and charge is in coulombs and time is in seconds. So current is charge per unit time. Here's the example from your textbook. It says the current in a light bulb is 0.835 amps. So when we write our given, we're going to write Q is I is 0.835 amps. How long does it take? And again, in this chapter, we're learning some new variables, or we're looking at some that we looked at in previous chapters. It's important, and at the end of the notes, I made a table for you. The reason I made a table is for all these variables, you want to know what is the name of the variable, the quantity. You want to know what the symbol is, and you also want to know what the unit is. So when you're reading a problem, if you're not sure, you can just, let's say, look at the unit and know that amps measures current. And what I'm talking about is if we flip to the end of the notes and we look here, this is the chart I'm talking about, where I have the word that we use to describe it, we have the symbol, we have what the unit is, and then we have the unit symbol. Okay? So this is going to help you, again, because there's quite a few different variables that we're talking about in this unit. Okay? So just remember that that's there, and you should be referring to it if you ever get confused. But you want to make sure you understand that before the test. And again, for me personally, when I see things in tabular form like that, it helps me to remember it, especially like when it's all together like that. All right, so when we look at this example, how long? So the key word is how long. So that means that we want to find the time. Does it take for a total charge of 1.67 coulombs, so now we're going to write that, to pass through the filament of a bulb? So we write our given, we write what we want to find, we find the basic equation that has those variables, and then we rearrange the equation to solve for the unknown in terms of the known. And then we substitute and solve. And that's it. Now in the next chapter, when we look at complicated circuits and stuff, we're going to see that understanding current and the way that current flows is the key to very easily understanding not only simple series and parallel circuits, but complex circuits, and you'll find it very simple, easy if you pay attention in class. All right, resistance. So the word resist in layman's terms means what? Kind of like hold back. Well, resistance, as far as electrical current, means the opposition to flow. So that makes sense, doesn't it? So resistance is the opposition to flow of electric current. So conductors have low resistance. So what do I mean by a conductor? So we had learned previously, like a conductor, something that conducts electricity. Metals are very good conductors of electricity, and certain metals are better conductors of electricity, like copper. And what that means is if they have low resistance, more electrons can flow through them easily. So they let the electric current move, and then insulators, like remember when we talked about tools, and we talked about all tools that are metal, that they have some type of an insulator on the handle. They used to have wood, but now they have plastic or rubber. So if you're using electricity, that electricity won't flow through the metal, and you won't get like a shock. Okay? Now the unit for resistance is called an ohm. This is named after George Ohm. And then this symbol here is omega. So that's the symbol for resistance. So resistors are used to control the flow of current in a circuit, and we're going to see these over and over again when we look at different electrical devices. We're going to be actually constructing circuits in the next chapter and using resistors. Now, resistance depends on 4 different things. So number 1 would be the length of the wire. So the best way to think about this is, think about if you had water flowing through a pipe. Water would be analogous to the current flowing through a wire. If I had a short wire or I had a longer wire, it's going to take longer for it to flow through the longer wire. The thickness of the wire. So if I had a pipe this thick or I had one this thick, isn't more water going to flow through the thicker pipe? Well, the same thing is with current. The material it's made out of. So if it's a really great conductor like copper, more electrons are going to flow more easily. And then if we have different types of metals, it's going to hinder the flow. And then the temperature of the wire. And temperature is something very interesting because there can be some wires that are good conductors at room temperature, but then as you heat them up, it changes the physical properties of the material. So what happens is materials at different temperatures, if let's say copper can lose some of its conductivity, so even though it might be a good conductor at room temperature, at high temperatures it may lose its conductivity. And then there's some materials that at high temperatures they might be good conductors, and those things are called semiconductors. So this is all important when designing something. Now we're going to learn Ohm's law. Now back in the day when I took physics, when we learned Ohm's law, it was in this format. So this is the way that I always remember to write it. V is equal to IR. So voltage, or potential, is equal to the current times the resistance. Now the way it appears in your book is like this. So they have resistance is equal to the change in voltage over I. This Ohm's law is the most important equation we're going to be using in the next chapter when we're analyzing complicated circuits. This is something that you should just remember off the top of your head all the time. But again, I remember it like this. V is equal to IR. This is the way it appears in your book. Obviously, it means the same thing. So here's an example. What is the current through? Now remember, whenever we do a problem, we want to chunk it. So as we're reading it, we're going to write down our given. So it says, what is the current? So we want to find I through a 30 ohm resistance. So R is equal to 30 ohms. That has a potential difference, so that's V. So I write my given, I write what I want to find, I write my basic equation, V is equal to IR. I rearrange the equation to solve for the unknown in terms of the known. And then I substitute and solve. Here's now an example from your book. The resistance of a steam iron, so they're going to give us R. What is the current? So I want to find I in the iron when it's connected across a potential difference of 120 volts. So we write our given, we write what we want to find, we write our basic equation, we rearrange the equation to solve for the unknown in terms of the known, and we substitute and solve. And then this is we're gonna continue for tomorrow. So that's all we're doing for today.